Good morning. Welcome to Krishna's class. Let us continue with the exploration of the structures of Hilbert spaces. Let us just recall. This was one of the questions posed by somebody in the chat, that what exactly is a Hilbert space? A Hilbert space is a recall a Hilbert space is a linear space over R or C, depending on which you call it a real vector space or a complex vector space, with an inner product defined on it. And further, the metric norm and the consequential metric induced on the Hilbert space on the inner product space makes it a complete inner product space. And this is what is called a Hilbert space. So a Hilbert space is a complete normed, complete inner product space. It's needless to say it is on R or C. Now we will go into more details of this. So what is happening is, so H is then what do you have on H an inner product. An inner product is a map from designated by and what is inner product? Is a map from sorry it's a map from H cross H to C. That means you have for X, Y belonging to H. It is mapped to a complex number there is a function. So it's a complex valued function on H cross H. With what are the properties? The properties that you have are X, Y such that conjugate. That's the first thing. Second thing is third property is that it. Fourth property is that greater than or equal to 0 and zero. That facilitates definition of a norm the positive square root of the inner product of x with x is a length function defined on and this induces a metric on H it induces a metric on H defined by xy belonging to H. And is a metric space which is complete. So that means H is a real or complex linear space over the fields R or C. I mean, that's what you mean by real or complex. Then an inner product is defined on it. As we have listed out the properties of the inner product, the inner product induces a norm on the Hilbert space. Norm means a length function. That means it attributes to each vector a length. And then using the linear space structure and the length and the definition of the length of a vector, we can define what you call a metric, which you can prove that it has all the properties of a metric. Okay, namely dxy is greater than or equal to 0, dxy equal to dyx. Then the third property is that d of dxy satisfies d satisfies the triangular inequality. All these things can be right. So it satisfies all the properties of the length function. dxy is equal to dyx. This is a symmetry property. dxy is greater than or equal to 0. dxy equal to 0 if and only if x equal to 0, and the triangular inequality is satisfied. That means dxy is less than or equal to dxz plus dzy for every xyz belonging to H. Now these properties are satisfied. Therefore, it becomes a metric space. Therefore, it's a topological space. Okay. Now, with this topological space is this metric space is a complete metric space. What does it mean? That means you take any Cauchy sequence of vectors in H, they converge to a vector in the space itself. Then you call it a Hilbert space. Suppose the last property is missing. That means all these things are there except the completeness. Then you call it just an inner product space. Okay. So inner product space is also a metric space, and sometimes it may not be complete. I mean, as you have already seen examples. For instance, C01 I looked at, it is not complete, whereas L2 mu is complete. I mean, these are the various, or Cn over C with the usual metric is complete. And there are, so they are all Hilbert spaces, but the first one I mentioned, namely that C over all continuous functions over 0, 1 with the inner product, with the usual inner product that you impose on that space is not. Okay, so that is merely an inner product space. Whereas the other spaces that we have considered as examples, they are all Hilbert spaces. So that's that. Now we go further from here. So now we consider three functions. Given H a Hilbert space. See, we consider the following maps. The first one is for x belonging to H, have x to for a given y, fixed. So this is this. Let me designate by fy. So this is the map fy, or you have fy of x is defined as this is the map that this is one map. The second map we consider for h belonging to x belonging to h, getting mapped to yx. That is, this is interchange. Role of y and x are interchanged here. So we call this gy. Okay, which belongs to C. For so you take any vector y belonging to H, it induces two maps on this, on H, namely Fy and Gy. Now, how is Gy defined? Gy of x is defined as the product of y x. This is the map. Now you see that this is an element of C. Therefore, it's a map from H to C. So there are two maps from H to C. Now we also consider a third map, then we will come to the properties of that. Okay? We will come to a third map on H, namely the norm. Okay? So we consider a third map, namely H from R. In fact, more precisely, 0 to infinity. Defined by norm of x. So this is the definition of H. There are three maps that we are considering. What are the properties of these maps? First of all, you observe that is alpha to x2 equal to alpha 1 fy this is quite easy to, because it comes because alpha 1 x1 plus alpha 2 x2 y equal to therefore fy is p. That is one property. P gy is conjugate linear. It is not linear, it is conjugate linear, or it is also called sesquilinear. No, linear. That is, you have gy of y alpha 1 x1 plus alpha 2 x2, where alpha 1 x1 and alpha 2 x2 are complex numbers. This is equal to alpha 1 conjugate this is it. That's quite easy to prove because this is how you prove it. This is equal to alpha 1 conjugate y quite easy to prove using the properties of, okay, for every c and say y is a fixed element. Thus, what we have is that every element y in the Hilbert space induces a linear functional as well as a conjugate linear functional on H. Okay, they are designated by Fy and Gy. The C is a definition is not is neither linear nor conjugative. This is an observation that you make. Neither linear nor conjugative. It's just a real value with certain nice properties. We shall explore this. Now we prove the following theorem. GY are continuous. In fact, uniformly continuous. Uniform. Or I will put it straight away here. Uniform. And H is also okay. So let us prove this. X1 minus X2, the inner product X1 minus X2 with Y. And this is by Cauchy-Schwarz inequality. The Y is fixed. Okay, this is true for Therefore, what do you get? It immediately follows that Fy is not only continuous, but it's also uniformly continuous. Because you have modulus of Fyx1 minus Fyx2 less than or equal to norm of y into norm of x1 minus x2. Now this is actually d of x1 x2. Therefore, this is a continuous function. It is uniformly continuous because y is a fixed element. So this is something like the Fyx1 minus Fyx2 modulus of that is less than or equal to some constant, which is the norm of y times norm of x1 minus x2. Okay. So from this inequality, it is immediately clear that Fy is continuous, uniform. This is the first one. A, B, similarly, Gy from uniformly. This is because Gy of this is equal to inner product of y to yx2 and this is equal to which is less than or equal to norm of y so from this inequality likewise Gy is see what about norm, what about h? For x1 belonging to h, you see that h of x2 and this is less than or equal. Now this is proved as follows. This is equal to, because all you write x1 as x1 minus x2 plus x2 and then group them and then use the triangular inequality. And this is less than or equal to this, and which implies in fact, you see, you have both. Similarly, norm of x2 minus norm of x1 is also less than or equal to norm of x1 minus x2. Therefore, together you get modulus of norm of x1 minus norm of x2 is less than or equal to norm of x1 minus x2. That means mod hx1 minus hx2 is less than or equal to norm of x1 minus x2. So that is done. Okay, and h is also a uniformly continuous function on H. So we have proved that here. Thus we have three functions now. One, you make the following premise. Every vector in H induces a uniformly continuous linear function on a uniformly continuous what is it? Fy a uniformly continuous conjugate linear function on functional gy on further the norm function is a uniformly continuous. Function on these are the observations that we make. So each y induces a linear functional as well as a conjugate linear function. What is a linear function? A linear functional is a map from H to C which is linear. Similarly, a conjugate linear function is a map G from H to C which is conjugate G. So this is what you infer. Okay. Now these are properties that are quite something that we look forward to. We make some more definitions which gives some insight into the lecture, into the structure of the Hilbert space. First of all, subspaces. For any vector space, not necessarily a Hilbert space, V for any vector space V, a subset M is a subspace if is a vector space over the same associated with what does it mean? Means that is with respect to the same and addition and scalar multiplication. Is close. That is alpha x belongs to M for every and alpha belonging to the associated. So, using this, we can talk about now subspaces of Hilbert spaces. I mean, that's our intention eventually. Okay. So, let us look at some examples. In any vector space, the set consisting of the zero element and V itself are so there are two trivial subspaces, namely the zero vector and the whole vector. For instance, in R, see R over R is a vector space, or C over C is a vector space. Now, there are exactly two subspaces there, namely the subset consisting of the zero vector and the subset which is the whole set. Okay, right? So that's an example where only those two are the subspaces of the space. That's an example. Okay, now we take something now. Let V be defined by the set of all F So f is a complex valued function on x. That means f is defined from S to C. Now we can define that, take the with the usual addition. and scalar multiplication. V is a vector space. Over C. So vector space over C. Now consider M defined by F belonging to B such that less than or equal to 1. Okay, first we will consider F is bounded. Then proper subspace of V. Now consider the consider so all complex valued continuous functions which are bounded by 1. X is not a subspace of P, because you can find X and Y belonging to or F and G belonging to X to some does not belong to the same class. So we give another example. And these are the only subspaces. The first one is R3 itself. The second one is all planes passing through the earth. Okay. And they form a all the planes that pass through the origin are subspaces. They are not trivial subspaces. Third one is all lines in none of these examples we are invoking the inner product or anything because we are not imposed it. Talking about vector spaces and not on inner product spaces or Hilbert spaces. Okay. The four examples, these are the only subspaces. Now, the first one and the fourth one are the trivial subspaces, and these are non-trivial subspaces. That means if you take R3, consider a plane passing through the origin. Take two vectors in it and add. If you add them, you get another vector in the same plane itself. Similarly, to take any vector in that space, in that plane, then any scalar multiple of that is also a vector in the same plane. And the same remark holds for lines passing through the origin. Now, this is three-dimensional subspace because R3 is three-dimensional. This is the three-dimensional subspace. These are all two-dimensional subspaces. These are all the only one-dimensional subspaces. And this is a zero-dimensional subspace. So, these are the four types of subspaces that you can have. Okay. You can generalize this. This is just to get a feel. Now we come back to the inner product space again. Come back to the inner space. So H is the inner product space that we consider. Now we can talk about, here you don't have any metric defined on the space because we have not defined any norm or anything, irrespective of whatever norm that you can impose on this or whether you impose it or you don't impose it, these statements do hold. Okay. Now let us, we are in a Hilbert space and therefore we have the facility of a inner product and consequentially a norm and which induces a metric. Therefore, you can consider some topological properties. Be a subspace. The Hilbert space H. Now, M is a closed subspace. H. If M is a closed is a subspace and Z close to subset. What does it mean? What does it mean? That is, any convergent vectors in M convergent in the limit is also, that is, suppose xn is a sequence in such that and xn converges to x belonging to h. Okay, because it is complete. I mean, if it's a convergent sequence, then it automatically converges to some element in H. Then this implies X belongs to. That means all convergent sequences in M converge in M itself. This is this then you call M a convergent, M a closed subspace. Now for any M, a subspace of H, we can define its closure. Okay. Be a subspace of closure consists of all those y belonging to H such that y is equal to limit n tending to infinity of yn is a sequence in so you take all sequences, convergent sequences in H, then M closure consists of all those y belonging to H with the property that y is the limit of sequence yn, where yn is a convergent sequence in M. That means this means the following: limit n tending to infinity this is the meaning. Okay, so you take all such y, or just take the boundary of M and induce and include that on this. Then subspace of, how do you prove that? Take closure. Then that means now you can prove that x plus y and alpha x belongs to M. Observe that because M is a subspace. Further, and that is because therefore so if x and y belongs to M closure, then x plus y belongs to M closure. So if x and y belongs to M closure, similarly this is because there is a sequence xn in M which converges to x, and then alpha xn converges to, this is because goes to 0 as n tends to infinity. So alpha xn, if x belongs to M closure, then alpha x belongs to enclosure. Therefore, enclosure is a subspace. Okay. Now I think that's a place where we can stop. And next time we'll take up the concepts of convex sets, orthogonality, and some consequences of that. Okay. Thank you very much.